Hello, everybody. March 7th, 2026. And one of the things that I'm going to do is share with you what I taught just recently up in Parma, Idaho. February 28th and March 1st, I was there doing an S211 class. It's been a while since I've done some training videos. The day job has been keeping me pretty busy. But you're looking right now at a book that one of three that I've written. Specifically, this one, you'll note the title, Understand the Capacity of the Mark III or any other pump. And the reason it says that is because we're going to be looking a little bit at pump curves and knowing how to take maximum advantage out of every pump. But this is something that I felt that should have been covered doing an S211, and so I did. It does not exist in the original NWCG publication. In fact, some of the hydraulic calcs that they use really are kind of. There was one that I proved in the actual instructor guide that I have from 2012, that the calculations that they use are actually technically wrong. They're incorrect. The method is the same, but the numbers are wrong. Anyway, so this here is about a 32 to 34 page book, I believe. I even cover the dangers of hydraulics and heat generation from a pump. In this book, I show you how to determine how much time, how quickly a pump will go critical at deadhead by using that formula. And then I give a brief explanation of head pressure, what it is, how to calculate it, why we know the pressures to use to calculate head pressure, then rounding numbers, the problems with that, friction loss, and nozzle pressure. And then there's some conversion factors in the back of the book. And then on the very back of the book, I have my Substack page, email address, main website, and cell phone number. So we're going to be talking about this, but the idea um, that I was presented with when I was in Idaho was not so much as how to teach the Mark III or portable pumps. It was how to determine if you could only obtain Mark IIIs, how you knew that a Mark III or a set of Mark IIIs could do a job. How to determine that, and so that's what we're going to go over here, and then that's what this Mark III pump capacity cheat sheet is all about. And this is 8 pages, and I have this on my website as well, wildfireengineer.com, and then. You can determine whether you got single line hoselay going up or parallel line, i.e., a Siamese. Um, and you can do all sorts of things with hydraulics, but this is going to give you. It's going to be real quick and dirty. It's probably going to be about maybe 15 minutes worth, no more than 20 minutes. It goes by really quick, and it's super simple. So basically, you start with your diagram like this, whether it's going this direction or your mountain's going up, whatever's convenient for you. It doesn't matter. But basically, what you need to do is, in all cases, you need to determine your elevation and your hose lay distance, how much water you want to flow, and then from there, you determine your pump discharge pressure, which is what number 3 assumes from this equation here. And then after you get the pump discharge pressure, then you can move into determining the number of pumps from the pump curve and then how far apart to space those. And that's what I'm going to show you today. So here in this example, a hose lay is 18,000 feet in distance and has an elevation gain of 2,000 feet. Branch needs to have 60 gallons a minute for BTU capacity supplied to keep up with the firing operation. Separate pumps will supply hand lines with nozzles, so do not factor nozzle pressure at 100 psi. The PDP would be 3136 for a single line and 1444 for parallel lines. When stage pumping, count nozzle pressure at 10 psi or less. Now, let me go over something really quick here, okay? Because this is kind of critical. When you're working with a hose line, okay, and you just have a hose and then the nozzle is removed, that's called an open butt connection. So figuring gallons per minute on an open butt, you use the formula of GPM equals 27 times the diameter squared times the square root of the pressure. Note, it says pressure, not nozzle pressure. Pressure. How much pressure are we going to shove through that line? But you could count it technically as nozzle pressure. So we're going to use an inch and a half line, so it becomes 27 times 1.5 squared times the square root of, we'll say, 10. Okay? So now if we do this, here's what this works out to. 27 times 1.5 squared times the square root of 10. You have, 192. So 20, I cleared it by mistake. Times 1.5 squared times the square root of 10 equals 192. So that means that the gallons per minute, if you had 10 psi, it would jump from, let's say, 60 to 192. Well, that's an impossibility. You're not getting 192 gallons a minute out of a Mark III pump or a portable pump. You're really going to have a hard time doing that out of most wildland engines, going up any hoselay or any length of hoselay or elevation. So use 1 psi. So if you go 27 times 1.5 squared times the square root of 1, then you have 60.75 gallons per minute. So I recommend using 1 psi for your nozzle pressure. Okay. So now that we've got that out of the way, let's go back to our problem. So again, we have 60 gallons a minute as our need. Always determine your need. The hoselay distance is 18,000 feet. Elevation gain is 2,000 feet. So let's pause right there and let's draw out our diagram. So from here, we've got this. Your head equals 2,000 feet. And your hoselay distance equals 18,000 feet. The GPM equals 60, and then the friction loss equals 12.6 per 100 feet. Now, how do I know that? I'm going to show you how we know that. Because on our cascade slide rule, which uses the arithmetic very well, okay, we have here, let me show this down here. 1 second here. 60 gallons a minute, okay, is underneath the arrow. See, set flow at arrow, 60. And then we come over and we look at, we have an inch and a half trunk line. And then because we're using a single line, not a parallel line, we read up and our friction loss is about 12.6 psi per 100 feet. So that's what we use, is 12.6. And that's what we got right here. So now, head pressure, I strongly recommend that above 600 feet in elevation gain, you do not divide this by 2. And I'm going to show you why, because you already know if you take half of 2,000, that's 1,000. So keep 1,000 in mind. So now, if we have this multiplied by 0.434, then the new head pressure becomes 868, which is what we're going to use. But that's a difference of 132 psi. That difference of 132 psi, if we were to write this out, so 132 times 2.31, because 1 psi weighs water, 2.31 feet. So if we go 132 times 2.31, that's a distance of 305 feet in elevation that you can gain that you otherwise wouldn't know that you're losing. Okay? So always use the 0.434 multiplier as much as possible. So your head pressure is 868. So now, friction loss. We already know what our gallons per minute is. Our friction loss is 12.6 per 100. We need to know the number of sticks or sections of hose. And how we do that in wildland, for those that don't know, is we take the 18,000 and we divide it by 100 feet to get the number of sticks, as we call it, which equals 180. So then we'll take the 12.6 and multiply it by the 180 for our friction loss to be, I believe it's 2268. So 180 times 12.6 is 2268. And then our nozzle pressure equals 1. So now you add this all up. 2268 plus 868 plus 1 equals 1337. So, or 3137, 3137 psi. That's PDP. Okay, so now what we need to do is determine the number of pumps required to move 60 gallons a minute up 18,000 feet of hose lay. Because a single Mark III sure as hell isn't going to do it. So you're going to need more than one, obviously. But that's the whole point of this exercise and showing you guys this is how you do it. So we're using real numbers, elevation and distance, and the friction loss off of our scientifically proven method. So we know that this is accurate to this point. So now what we need to do is we go back and we introduce, and I recommend that you people get a copy of this and print it out. What you do is you get a hold of the pump curve for the Mark III, and you see on the bottom it's got gallons per minute, and it's got friction loss per 100 feet of hose. So you can see right here, friction loss on 60 gallons a minute through through a single hose lay is 12.6 psi per 100 feet. So it pretty much gives you this already. So, and this one I added, but 60 go up to the limit line, which is the gray line here for the standard Mark III. The red line is for the Watson edition. Um, and then as soon as you hit that, come over to the left. You got about 165, 170 psi. That's what I'm going to use is 170. So this is called the pump curve pressure. Okay, and this is critical because out of this pressure, let's say 170, you have to be able to supply your head pressure, your friction loss, and your nozzle pressure, whatever that may be. So just keep that in mind. This gets eaten up very quick when we're going uphill. So 170 is going to be that. Okay, so let's write this down up out of the way here. So pump curve pressure equals 170 psi. Okay, so now what we do is we take PDP divided by pump curve pressure, we'll call PCP, equals 3137 divided by 170 equals 3137 divided by 170 equals 18.45. That's the number of pumps. So number of pumps equals the pump discharge pressure divided by the pump curve pressure equals 3137 divided by 170 equals 18.45. Well, you're not going to get 45% of a pump, so you have to round up to the next whole pump. So you get 19 pumps. Okay. Now, to determine pump spacing, equals distance divided by number of pumps equals 18,000 divided by 19 equals 947 feet. Now, up to that point, that's been for a single hose lay. If you want to determine the number of pumps required, if you run a parallel line from this point to this point, then what you need to do is take your friction loss here and divide it by 4, because a parallel hose lay has 1/4 the friction loss of a single. So if you take 2268 divided by 4, it comes up with 567 psi. So I better double check that. So 2268 divided by 4, yep, 567. So now if you re-sum this up and go 868 plus the 567 and 1, That's where you come up with that 1444 psi, I believe. So 868 plus 567 plus 1 equals 1436. So now for parallel lines equals PDP equals 1436. Okay. And so number of pumps becomes PDP divided by the pump curve pressure, same as before, equals 1436 divided by 170 equals 8.4, round up 1 to 9. So 9 pumps. Now the distance, um, or pump spacing, pump distance, we'll call it, pump distance, equals the distance divided by number of pumps, equals 18,000 divided by 9 equals 2,000 feet. Plain and simple. It's literally that simple, folks. Now, there is another thing that you could do if you don't have a particular flow. Let's say you've got a fire and you want to determine, okay, well, how much um, how much water do I need to supply based upon the energy that's being developed by a fire. So let's say that you've got, somebody on the fire is a fire behavior analyst, and you overheard them saying that, hey, our intensity of the fire is, you know, 2200 BTU per foot per second. Okay, so here's what this means, okay? Um, let's say that you have a fire that's producing um, 2200 BTU per foot per second, and they're actually moving at a rate of spread of 1.5 feet per second. So let's say that this here is 1.5 feet, okay? But that gives you 2200, okay, BTU per second per foot, okay, because it's moving at 1.5 feet per second. So you could get the heat per unit area by taking 2200 and dividing it by 1.5, and it would actually give you about 1466 BTU per foot. Okay, that would be the BTU per square foot. But for right now, instead of confusing you with all that, let's just keep it at 2200 BTU per foot per second, which is 1.5 feet per foot per second. That's its rate of spread, 1.5 feet per second. So then what you would do is you would then multiply this by the distance that the fire is. So let's say it's 1.5 feet, okay? And then the fire is 500 feet, okay? So you would take the 2200 times the 500, and that would equal 1,100,000 BTU per second is what that fire is generating. Okay, so how much water do we need? Well, here's the trick. A 1-inch nozzle at 20 GPM equals 3,120 BTU per second. A 1.5-inch nozzle at 60 gallons a minute equals 9,366 BTU per second. So if you want to be able to determine the amount of water in gallons per second you need for a particular fire, you get its BTU per second per foot, multiply that by the length of the fire, get that figure, which is going to be this number right here, and then divide that by the 9366, and you need to deliver 117 and a half gallons per second. So this is where understanding the capacities of your pump, your nozzle, air resources really comes into critical. You can better match cooling resources to a fire if you understand the thermal capacity of water and how to calculate it. Now, I'm not going to cover that now, but if you want to get this book, you can go to my website and you can get it. And all of the lessons that you can learn are right there. 14 lessons, including pump theory and the introduction, a quick reference section, and then relay procedures, how to draft friction loss, calculating pump pressure, calculating heat generation and absorption. If you want to know how to do what I just showed you, you can go to wildfireengineer.com and or you can go to wildfireengineer.online, which is the online store, and you could pick up the books. So you can get this as a combined 144 page, 148 page lesson book with the quick reference, or you can get the quick reference standalone, and you can even get the standalone understand the capacities of the market. Anyway, that's it. Hope you guys enjoyed this, and give me a like and a subscribe if you found it helpful. And if you have any questions, you want to know more about it, certainly hit me up, email or text. Either way, it doesn't matter to me. Cheers. Be safe.